Okay, today algebraic, sometimes called Cartesian vectors, and some important moves here and vectors that's going to make a lot of the stuff we do much easier. So analytic geometry is what we're going to be talking about here. French philosopher and mathematician René Descartes, back in the late 1500s, early 1600s, along with Pierre de Fermat, founded a branch of mathematics known as analytic geometry or coordinate geometry. It's basically working in the Cartesian plane, what you've been doing all the way since grade 9. And this field of mathematics links algebra and geometry. We will soon see how this connection can be applied to geometric vectors, and as a result, how I don't know about some. Let's go with most operations can be made easier. So Cartesian vectors. Algebraic vectors or Cartesian vectors, so now here's the definition of what today's lesson is about, are vectors referred to in a particular coordinate system, such as that they can be described by their components in directions at right angles. Way later it might not be right angles, but we're going to really stick to right angles. This representation of vectors allows us to describe vectors as ordered pairs. So if you look ahead at the example that's on the screen there, they've got some vectors on the Cartesian plane there, and the vectors are referred to with just two coordinates. At first glance, you might think, oh, that's going to be confusing with regular coordinates because it just looks like how we wrote coordinates when we just write points. But it won't be confusing because there'll be something in the question or in what we're doing that'll tell us whether we're talking about vectors or points. You'll just have to trust me that that's not going to be an issue. You'll be able to know which one you're talking about by the nature of the question. Okay, so notation. In our familiar Cartesian coordinate system, x-axis and y-axis, an algebraic vector is denoted by an ordered pair a comma b, where a and b represent the x component and the y component respectively. So for instance, take a look at this vector here. It's 5, 2. And the reason it's 5, 2 is because it goes 5 to the right and 2 up. It's basically just giving you the run and the rise in that order. I know you're used to rise over run, but here we're going to do the x and then the y. And so this vector here, it goes left 4, so we got -4, and then it goes down 3, which is -3. This one here, left 4, -4 on the x, and then 2 on the y, and then so it goes up 2. And this one here, 1 on the x, so it goes 1 to the right, and then down 3, so it's 1, -3. An easy way to write vectors as a Cartesian vector with just two coordinates. The coordinates tell you the x and the y. Now, square brackets are frequently used to help us. So sometimes instead of writing, see this one up here was -4, -3, sometimes we'll use square brackets as a hint that, yes, we're talking about a vector there. So that's one of the tricks available to us to make it clear when we're talking about a vector instead of a point. So when round brackets are used, the context of the problem will determine whether the ordered pair represents a vector or the coordinates of the point. It might be this simple. It might say, graph the point, blank, and give you the coordinates. Or it might say, draw the vector blank 4, 3, and so then you know right away. So as soon as you're talking about a problem, you'll know whether you're talking about a vector or a point. So don't worry too much about that. Just watch what happens. Now, equal vectors, recall that equal vectors have the same magnitude and direction. So when working with algebraic vectors, we see that if two vectors have the same components, they will have the same magnitude and direction. So equal vectors have the same components. For instance, if I wanted to do a vector here that I'm going to do like this, and I've drawn the vector 2, 4. And then if I drew the vector over here as well, this vector would also be 2, 4. So the fact that they're not in the same spot doesn't matter. We still call them equal vectors. And as the chapters go along, you'll see why that has to be, that these vectors have to be considered equal when they have the same components, even if they're not at the same spot. So this question said draw 3 of them. So here's the third one. 2, 4 is my third vector there that's equal. So equal vectors do not have to have the same location. Let's just highlight that because that might be a new idea here. Two vectors do not have to have the same location to be the same vector. So a position vector is a very specific vector. Any vector A, B in the plane can be shifted so its tail is at the origin. And the shifted vector is called the position vector. So if the tail is at the origin, then the components of the position vector are the coordinates of the point of its tip. What do I mean by that? Here, check out this one. Here's a random vector, 5, -4. Draw the corresponding position vector. So the corresponding position vector would look something like this. Because its tail is at the origin. So what's interesting about this vector is still called 5, -4, but it ends at the point 5, -4. And that's why we call it a position vector, is because the vector ends at the exact point that is the same coordinates of the vector. Determining the components of a vector. Find the components of the vector with its tail at point 1, 2. So I've got to start this vector at 1, 2. That's where its tail is. And its tip is at 7, 6. Right there. And so there is the vector I'm talking about. Its tail is at 1, 2. And its tip is at 7, 6. And so if I want to find its components, how much the x and how much the y is, well, I'm just doing what we did for slope, which is delta y and delta x. The component of the x is the delta x, and the component of the y is the delta y. If that's confusing, what I mean is we just go, 7 minus 1 for the x, and 6 minus 2 for the y. See, that's a x2 minus x1 for the x component, y2 minus y1 for the y component. And so I get the vector 6, 4. Maybe you could have just looked at it and seen that, but we're going to be moving forward to 3 dimensions and so on. So we're going to want a system here. And the system, to find a vector AB, if you want to find a vector AB, just subtract the x's to get the x component, subtract the y to get the y component. That example there shows exactly why that works. Okay, all of that set up, everything we've been doing so far was to set up our introduction to 3-space. All the way through the grades, it might have occurred to you that, well, this is all fine that we're graphing these things in 2D, but so many of things in life are actually 3D. How are we going to jump to that? Well, the answer is actually pretty simply, we've set up the algebra in such a way that jumping to 3D is not going to be a big problem, algebraically. Visualization is a huge problem, monstrous. We're going to spend 2 chapters on trying to visualize things. So don't get too excited about the visualization just yet. Although I have uploaded another video, take a look at it, that will help you with visualization. So take a look at that video, go back and forth between the 2 videos to get some of the visualization here. So 3-space. Up to this point, we've only considered Cartesian vectors in the xy plane. The 2-dimensional coordinate system is known as 2-space, or R2. So it's got a new name now. Everything we've been doing up till now is called 2-space or R2. And the reason we say R2 is that we're giving 2 numbers whenever we're talking about somewhere on the coordinate plane. A point, say 7, 2. See, there's 2 numbers. And so that was where the R2 comes from. Points in 3-dimensional space can be coordinatized in a similar manner. The 3-dimensional coordinate system is called 3-space or R3. Well, whatever room you're sitting in to look at this video, just look at the floor right now. And imagine that we did all our math from grade 9 on the floor. That would be R2. We'd be graphing x's and y's all along the floor. All we've done now is you're allowed points that are not on the floor, but in your room somewhere, up in the air. So it would have 3 coordinates. Yes, an x and a y that tells you where in the room to be, and then a z to tell you how far off the floor to come. That's the easiest way to visualize what's happened here. And that matching up, it takes a while to be able to look at a picture like this and be able to visualize what's happening. But that is exactly what that picture is trying to show, is that x and y is sort of flat on the floor, and then z comes up out of the floor. Again, check the visualization videos if you're having trouble with the visualization at all. And the right-hand rule as well. I posted a link about the right-hand rule, so I'm not going to say too much about the right-hand rule here. I'll just say see video. Because it's not easy on a 2-dimensional page to talk about this right-hand rule. But the coordinate system, this is another version of the picture from up here. So if you had trouble with this picture, if that's a question mark, then check out this picture, because this really helps with the visualization. I mean, the videos are way better, but this is a nice vision of what's going on here, is that we had an XY plane that was sort of flat like that, and then there's these other planes now, the YZ plane and the XZ plane, that we could work in, and so that gives us our 3-dimensional space. We often draw it like this, in the circle there, but what we're visualizing in our mind is this picture here, which is not easy to draw quickly. So, a weirdly easy question that is extremely difficult, and I hope you know what I mean by that, is that it's really hard to visualize what this question's asking, but once you see it, it's a really simple answer. If we wanted to find the equation of the xy plane being the plane that we've been talking about all through school, that plane right there, that xy plane, if we wanted to come up with an equation of it, what's true about all points in the xy plane? They all have their z value equal to 0. Now that's a major introduction to next chapter. is when we're going to talk about the equation of these planes. So don't get too wound up about that right now. I just mention it to start laying the foundation for next chapter. Well, except for the visualization, life's pretty straightforward here. A point in 3 space is represented by an ordered triple. And similarly, Cartesian vectors in 3 space are denoted by ordered triples in the form x, y, comma, z. So in the diagram here, which is really hard to draw and picture, but maybe you can look at it for a second and visualize what the vector -5, -7, comma 2 would look like. And it goes -5 along the x-axis there, and it goes -7 along the y, and then 2 up. And you got to draw this rectangular prism to be able to really visualize what's happening. And so that's difficult. That visualization is very, very difficult. But to actually write the vector -5, -7, 2, that's pretty easy. You just add a z component to it. So there's an easy part to this, jumping to 3 space, is that just that third component. Determining a components of a vector in 3 space, well, the great news is here there's nothing extra here. If you want to find the components in 3 space, you just subtract the x's, subtract the y's, and subtract the z's. And that's all we're really asked to do here, is it says, find the vector AB here, and what I do is I subtract the x's, 7 subtract -1. I subtract the y's, 2 minus 5, and I subtract the z's, -4 minus 3. Just like that. 8, -3, -7. Let me just check those numbers there. 8, -3, -7. That's it. Okay, so not too crazy here to get started in 3 space. My screen's jumping on me. But take a look at that homework and take a run at it, because starting to visualize in 3 space is important. So definitely take a look at that other video link so that you can see a little more visualization there. Have a great day.